Inverse. This part is from section 2.2 and 2.3. It's about computing matrix inverse. Let's first look at the definition. So we're going to define, given a matrix A, what is invertibility and what is inverse of A. So first look at something we already learned from high school or middle school. So similar definition is reciprocal. So I can say, suppose A is a number, a scalar, is invertible if there exists a number C satisfies A times C equals C times A, which is 1. And in this case, C can be written as A to the negative 1, or its inverse. C is inverse of A. So for example, if I give A equals 2, then we find C is 1/2, which satisfies A times C makes 1, or C times A makes 1. So that means C is reciprocal or inverse of A. So reciprocal. So in that case, we can write C as A inverse. Excuse me. Now we look at following. So now A is n by n square matrix. It's not necessarily 1 by 1. In 1 by 1 case, this is the same as reciprocal. So for a square matrix, it is called invertible if you can find another C, such as CA equals AC equals I. And in that case, this C is exactly inverse of A and denoted by A inverse. But not every time, not every squared matrix A, you can always find C satisfying this invertibility condition. So if A is not invertible, then it's called singular matrix. For example, for any number, it's not every number invertible. For example, if I give A equals 0, then what is A inverse? Does not exist. In other words, this is a singular number. So a singular matrix is a matrix whose inverse does not exist. Now look at this example. We are given matrix A. At the end, we're supposed to ask what is the inverse of A without giving the answer, but the answer is given here, C. So its inverse is given, and we want to check their inverse to each other. So what it means is we want to check this identity. So if CA equals I or not, or AC equals I or not. So we can look at AC first, which is 3, 4, 5, 6, and negative 3 to 5 over 2, negative 3 over 2. So 2 by 2 matrix multiplied by 2 by 2 matrix. This is another 2 by 2 matrix. So we're supposed to have 4 numbers to compute. So the first number comes from this row, this column, which is negative 9 times 10, which is 1. Similarly, we can check all 4 numbers step by step, and this is exactly identity. We can also check CA equals I. So in this case, we can write C as A inverse, or you can write A as C inverse. Now we're going to mention one of the application of the inverse matrix. So suppose A is invertible. And if you want to solve AX equals B, a linear system, then from before we learn inverse matrix, what you want to do is to solve AX equals B, we reduce augmented matrix to RREF. Now, if A is invertible, in other words, A inverse exists, there's alternative way to solve the solution X from AX equals B, which is simply multiplication of A inverse times B. It is very likely analogous to look at a linear equation like AX equals B. Suppose A is number, B is number, then what is X? Then what you do is we divide A both sides. So X equals B over A. But in matrix, there's no division. Instead, you can write this as A inverse B. So in matrix, we can talk about its inverse. So A inverse B. This is exactly the same as here. Now we're going to solve AX equals B, where A is given it as 2 by 2 matrix, exactly the same as this matrix, 3, 4, 5, 6. And we know its inverse. This is its inverse. So now we're going to use this inverse to solve for AX equals B. So what you do is multiplication A inverse times B, and this negative 3 to 5 over 2, negative 3 over 2, and B is 3, 7. Now looking at first row and column, negative 9 plus 14, and second row and column, which is 15 over 2 minus 21 over 2, negative 6 over 2, so it goes to negative 3. So this gives the answer, solution. Now next, we're going to look at the most important part of this lecture, how to compute A inverse. So there's 3 steps. So the first step, you want to form an augmented matrix formed by A itself and identity with the same size. And then we do EROs, row reduce, until you get identity matrix. So identity matrix for the first part, and then some other part. And this some other part, the other half, the second half of the REF is exactly the inverse of matrix. If you cannot have REF of this shape with the first half identity, then it doesn't have an inverse. So simply speaking, if you have A, I, so to compute A inverse, we're going to work on this augmented matrix, AI, and try to do many EROs, and at the end, you want to have I for the first half, and the second half is some other matrix. So this guy goes to A inverse. If you cannot get this part, then identity matrix for the first half, then it's not invertible. Let's look at one example. So we first recall what elementary matrix is. An elementary matrix is a matrix that is obtained by performing a single ERO on an identity matrix I. So the first question is A an elementary matrix? The answer is yes, because to check if A is elementary matrix, we should look at 1, 1, 1 identity matrix, and we ask ourselves, is there any ERO, just one ERO, which makes the matrix, identity matrix, to A? The answer is yes, because if we look at first two rows, then they're the same. And the last row, the only thing changed is 2. And this 2 can be obtained by multiplying the first row by 2 and add it to the third row. So this is twice of R1 plus R3, replace R3. So the answer is yes, it is elementary matrix. Now the second question is, what is inverse of A? Now we are going to use our algorithm. So the matrix A is 1, 0, 0, 0, 1, 0, 2, 0, 1. Now to compute A inverse, what you do is we look at AI. We first write this down. And the other half is I, identity matrix, 3 by 3. Now we do EROs. So if we look at the first column, this has to be pivot. And we need to kill this by doing R3 minus twice of R1, replace R3. And by this ERO, we have the first two rows will be the same. But the third row is 0, 0, 1 and negative 2, 0, 1. And then we look at second column. First column we have pivot. Second column, this is pivot. And third column, this is pivot. So we already have staircase. So this is REF. If we look at each column of pivot, then those pivots are ones, the only ones on its column, otherwise all zeros. And this is identity matrix. This is exactly what I is. In other words, the other half has to be A inverse. So the answer A inverse is 1 0 0 0 1 0 negative 2 0 1. Is A inverse an elementary matrix? So we have A inverse. Is it elementary matrix? So we ask ourselves, can you find some ERO applying to identity and get A inverse? And again, the first two rows, first row, second row, they are the same. The only difference is here. So you get negative 2 here, actually. So what you can do is multiply by negative 2 to the first row and add it to third row. So R3 minus 2R1 replaced to R3. So the answer is yes. Alright, there is some propositions we want to present. If A is an invertible matrix, then A inverse is invertible, and A inverse equals A itself. So if you do twice inverse, then it goes back to A. And AB inverse equals B inverse A inverse. It is very similar to this formula for transpose. AB transpose equals B transpose A transpose. And if you are going to take inverse of A transpose, then this is the same thing as A inverse transpose. There's some equivalent statements. So if A is M by M matrix, the following equivalent statements are equivalent. It's called invertible matrix theorem. So if A is an invertible matrix, then A has to have n pivot positions. And in terms of linear transformation, so suppose linear transformation is given by matrix A. Then very often we are going to ask, is the linear transformation is 1 by 1, 1 to 1, or onto 1 to 1 or onto. So in M by M matrix, if A is invertible matrix, then it has to be 1 to 1 and it has to be onto. But if A is not invertible matrix, then A is not 1 to 1 and is not onto. So we can deduce from this invertible matrix, A if is not invertible or singular matrix, then the linear transformation given by A is not 1 to 1, is not onto. You can reject both questions. Alright, now let's look at following question. Find the inverse matrix of A. Now maybe I want to add one more question. Is linear transformation T given by A onto and 1 to 1? Onto, and is linear transformation is 1 to 1. In some textbook, onto is called surjective. 1 to 1 is injective. So those are equivalent terminologies. And if a linear transformation is one-to-one and onto, then we call T as bijective. So surjective, injective, bijective. So this is definition. All right. Now first we are going to look at inverse of A. So if there exists inverse of A, then we can say yes for Q2 and Q3. But if there's no inverse of A, then we can say no for both. We cannot have one yes and one no for Q2 and Q3. They always have the same answer for squared matrix. All right, so to compute A inverse, A is given by 1, 0, 0, 0, 1, 1, and 1, 1, 1. So we look at AI, augmented matrix, and try to copy the original matrix A and 1, 1, 1 identity matrix and reduce it. So to reduce it, first column, this is pivot, this has to be killed. So what we do is R3 minus R1, replace R3 and get 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0. So first two rows are not changing, but here this is changing, and this is 1, 1, and the negative 1, and 0, 1. And next we move to second column, and this is pivot. This will be killed by doing R3 minus R2. So the 0, 1, 1, 0, 1, 0, just copy first two rows, and this has to be 0, and negative 1, negative 1, and 1. All right. Now we can check the ERO shape. So this is staircase. We have staircase, and then it goes down here. So the pivot is here and here, but the next pivot is not in the third column, it's in the fourth column. So we cannot, that means we cannot change this. It's not equal to I, identity matrix. We cannot change the first half into identity matrix. This means, this implies there is no inverse, or you can say A is singular. Now if A is singular, then the answer for Q2 is TA onto, is TA surjective? No. Is TA injective? No. All right, we stop here.